Okay, so the last speaker for this session is Ian Roberts, and Ian works at the company AeroTex UK, which is based in Farnborough in Hampshire, in the southern part of England.
Okay, thank you. So this is going to be a lot different to all these other presentations. I'm an engineer, not a mathematician, so don't shoot me for it. So this is going to give a general overview of the issues that we face for in-flight icing and the analysis related to that. And just as a disclaimer, as it's giving a background, this isn't all my work. This is a lot of people's work over the years, so I'm just saying that this isn't my work that I'm presenting necessarily. So if we look at the history of in-flight icing, so it was known from very early on in the 1920s about that there were issues with icing, and of course back in those days they thought, oh, we'll just fly into the icing conditions, and someone went up with a sketch pad and drew the ice that was forming on the wings as they were flying through it. So they recognised at this early stage that there were significant issues. So there's carburetor icing, we've got drag increase. So they recognise the difference between the rime ice and the glaze ice. So you get these at warm temperatures where the water doesn't freeze instantaneously. At warmer temperatures and at colder temperatures it's more conformal. So they were developing a good understanding very early on. Okay. Hello? Okay. So they rapidly expanded. So this is a icing wind tunnel in the 1930s, and they developed all these spray valves to give the correct droplet distributions and things. So things were moving quite quickly. They were developing ice protection systems, so they had inflatable boots. They were putting fat onto the propellers to keep the ice from forming on them, all sorts of things. But during the 1940s and 50s, NACA, so the predecessor to NASA, did a lot to define the icing envelope. So you can see this aircraft here. It had a range of cylinders on it. So the droplets are generally in the region of 15 to 40 microns. And because of the different cylinder sizes, they would collect ice, and then they'd be able to determine from the impingement what sort of droplet spectra there are in the atmosphere. And so they produce these standards which give different forms of ice. So this is stratiform cloud, so it shows temperatures going down to Fahrenheit -32, so -25, -30 degrees, and up to 22,000 feet, and quite high volumes of water, so 0.8 grams per meter cube. And these are like old figures, but those are still in the certification standards today. So it's things haven't moved quickly. This shows the cumuliform clouds. So you can see that these are much shorter duration encounters that the aircraft have with them, but you get much higher water contents in them. So that was the case for a number of years, but then more recently there've been a number of issues that have needed to be addressed by the icing community. So the first one is supercooled large droplets. So this is associated with the presence of large droplets. So this is illustrated here. So this is your typical ice being around 50 to 50 microns. But supercooled large droplets can go up to 2 millimeters in diameter. It was actually known about very early on, but when people looked at it, they said it's not really a problem. So it was never put into the certification standards apart from the UK ones. Unfortunately, in 1994, there was an ATR aircraft, and what happened is these large droplets, they get less deflected by the airflow, and they impinge directly after where the ice protection system is on the leading edge of the wing. So large amounts of ice grew, and unfortunately the aircraft was lost. It lost control and crashed. So this was an issue that the community started addressing. So the supercooled large droplet comes into two forms of freezing rain and freezing drizzle. So freezing rain has a maximum diameter of 2,000 microns and an MVD, so mean volumetric diameter of 400 microns, because it's a distribution of droplets. And what happens in these conditions in the atmosphere, you start with snow or ice crystals in the high atmosphere. It goes through a warm layer, which melts the outside, and then it goes into a cold layer again. So you're left with these supercooled large droplets in the lower band. For the freezing drizzle case, so this is mean diameters of 100 microns and up to 500 microns. They can be produced in the same mechanism, but what they tend to do is with collision coalescence. So these droplets collide with each other to gradually form the large droplets. It tends to be at warmer temperatures, up to from -12 degrees C and above. And then these are the certification standards that show the sort of droplet distribution. So these two are freezing drizzle, so we're looking at 500 microns here, whereas this is freezing rain, which is over 2 millimeters. So most of the time with the supercooled, for standard droplet icing, that you just assume all the water is collected on the wing. You've got a film of water or ice and it just impacts on the wing. But under supercooled large droplet conditions, you get the two different conditions. So you get, you're at a very high normal velocity to the surface, you get the splashing, and if you're at a very low angle, you get this glancing angle, and you get a bounce of the droplets off the surface. So this is as far as engineers go with mathematics. So this is there was some work done to try and quantify these losses, and so it's a function of the Onnesauge number and the Reynolds number, and this was largely correlated to specific tests that were performed to try and characterise it. They had the basics behind it, but then there was lots of correlation parameters put in. So you end up with a mass loss on the splashing terms and a mass loss on the bouncing terms as well. So we took those equations, put them in our codes, and happily enough, so you've got the black line, which is the experiment. These red and green lines are our codes that we normally run, and then when we put the corrections in, you get, so this is the leading edge, and this is the, not very clear there, this is the amount of water that's impinging on it. So you get this loss at the leading edge, where it's normal to the flow, and then you get this bouncing effect further away, where it's a sort of more glancing angle. Of course, that's the nice one that works very well. There's lots of different aerofoils that you could put in, and it's not quite so nice. But there's work being done, so the AIAA, which is the one of the big aerospace institutes, is looking at, has a nice prediction workshop where the whole community is working towards improving the modelling. So once the droplets, these large droplets have hit, they've splashed or bounced, you can then get droplet re-emission. So this was what we're talking about, droplets going back out into the flow after they've hit a water film or something. I won't go into a lot of detail on this because this is still emerging work at the moment. There's lots of proposed approaches, but they're looking at, for instance, breaking down the normal pit into a normal and a tangential component. So you've got the splashing, you get a radial distribution of the velocity, and then the droplets that come out, they can come out, as you get with the classic milk splash, they can come out anywhere in 360 degrees, but the angle that they come out with from the surface is between 0 and 25 degrees. Again, it's a lot based on empirical fits for this. And then, in terms of the tangential component, you just take a simple damping and assume 20% of the energy is lost during the interaction. And for the bouncing case, it's effectively just coming down to the tangential component. So it comes, basically you get the normal velocity coming out from the surface is either between 0 or 0.83 of the incoming velocity. So the main issue for aircraft is probably something that people haven't realised, though, is that the new regulations came in 2015, and I don't believe at the moment that there has been a new aircraft that has been certified for these standards since then. So we're talking almost 10 years, and no aircraft can be certified against the standards. So obviously this new aircraft's come out. And what they have done is to have a detect and exit, so they're allowed to be able to say, we're in these SLD conditions, we've got to leave. Derivative aircraft, so if you've got your Airbus A320, you can do tweaks to it, and that's fine. But if Airbus comes along, or Boeing, or whoever, and says, this is a completely new aircraft, it's very difficult to prove that they meet the standards, because there's no way of proving it. And one of the main reason is the facilities. So we've got big icing wind tunnels all around the world, but producing these large droplets is a big, big problem. So if you've got a spray bar, it sprays the water out, very large droplet, it's affected more by gravity, and it doesn't even reach your model, it ends up with a puddle on the floor with the droplets. The droplet temperature may not stabilise, so if you've got the droplets have to be sprayed in at a positive temperature to stop you blocking your spray bars, so they're at, say, +10. But if you've got a very large droplet, it takes longer to stabilise in temperature, so it might not reach the temperature. Before you get to the working section, there's a large contraction. That can cause shear flow, which breaks up the droplets. And also just injecting the droplets in the first place, they can break up. So there's a lot of problems. So one possible solution, this is something that HONORA, the French government research agency, has done, is to turn the wind tunnel on its side, and so there's no gravity effect, so it doesn't fall out. And then they've got a great big long expansion of the working section. The main issue with that is you end up with a huge boundary layer developing on your wall. So they've got a section that's maybe just very small, 20 centimetres by 20 centimetres, but only a fraction of that is not boundary layer. So it's lots of problems still to overcome. So if anybody wants to build a new wind tunnel, I think they did an estimate and it would cost about £500 million to do an aircraft-sized one. So the ice crystal icing is another term area completely. So this is where you've got these large mesoscale convective systems, basically lots of thunderstorms that are coming together, and we talk huge thunderstorms that can be 100 kilometres across. So this is mainly in the tropics region, and what these do is they lift huge volumes of water very high into the atmosphere where they form ice crystals, and these might be pure ice crystals or a mixture of ice and water, but generally they occur at sort of 33,000 feet or above. One of the most unfortunate incidents was a few years ago. There was a flight from Rio to Paris that crashed in Air France. 228 people were unfortunately killed. And what happened was that the pitot tubes, so what you use to measure your speed, they became blocked by ice crystals, and they lost their bearings effectively. There were some other errors associated with pilot's awareness, but that was sort of the thing that triggered everything. Generally speaking, it's not a problem for your wings. If you've got an ice crystal, it's hard, solid, bounces off. But if it goes into a hot atmosphere, such as your pitot tube, because they're typically heated to 300 degrees C, or if it goes into an engine, you can start getting ice forming. And there's an example video here. So this is inside an engine, so it's just after the sort of where the main fan is at the front. And you can see there's this ice, it's very slushy sort of ice, it's not a consistent ice, and it runs and forms. You've got your blades here and it's growing up all along them. This isn't an in-service engine, this was modified to be able to do this, so you don't need to worry too much, but there are incidents of you're getting rollback of the engine, so they need to restart it and things like that. So it is a significant issue that is being addressed. So in terms of the a bit more of the physics, so the ice crystals can be very large, sort of 2, 3, 4, 5 millimeters. A lot of them get broken up when they go through the fan at the beginning, so you end up with smaller, sort of 20 microns ice crystals that go into the engine. What generally happens is they'll come in here, and it's in this front low pressure compressor stage where the ice crystals start to form, because it's a warm area of the engine. So what's happening in these conditions is that the ice crystals are melting, so they're getting a water layer that's forming on the ice outside of them. But as it says here, it can either be melting on impact with a warm wall or during its transition into that part of the aircraft. So droplets have been known for years. They're nice, they're round, it's easy mathematics. So, but when you consider ice crystals, they can be any shapes. You can get sort of column-based ones that look like classic snowflakes or anything like that. So they can be a whole load of shapes. So it becomes a lot more difficult to model their transition. There was some interesting work done by Hulk et al. Referenced there, and they actually took some ice crystals and they put them in a levitator, and so they could see them changing their form. What this basically gave them is we're engineers, so we like getting it back into a sphere, so we get a sphericity parameter. We've got a porosity parameter, which says how much air is in there, and then there's this surface blowing factor, which is related to how much heat transfer there is between the crystal and the mainstream itself. But these, of course, are highly transitory because it's melting quite quickly. So this is some of the pictures from the levitator. So going from left to right, you can see them changing from an ice crystal into a sphere in the levitator. So when we consider the ice crystal melting, the models are effectively given in 3 phases. So you've got your full solid ice crystal phase, sort of some basic temperature equations and mass conservation. It then goes through a melting phase where we've got this factor MR, which is the melt ratio, which is the relationship between the amount of solid crystal and the amount of liquid phase. And then we go into the fully liquid phase. This is just presenting an overview, so I'm not going to go into lots of detail about it. There's some references there that you can look into. But once you've done all this melting, they then impinge on some surface And so when you do that, they can cause further issues. So you can get ice crystal ablation. So the ice crystal actually hits and it chips off a bit of the ice that's accreted on the component. So you can end up with sort of very pointy shapes on your bodies. But there's also a sticking factor. So this is quite a lot of work that's been done at Oxford on this. And so there's this melt ratio which gives optimum sticking factor of about 10%, is what you need for the ice crystal to fully stick. So effectively you've got these limits so if you've not enough ice to cool the surface to the freezing point, I don't know why it's a cool surface, so it applies it probably. And then there's not enough water to produce sticking, so it's this. It's quite a fine balance between the two. Again, like the SLD, you're going to need whole new test facilities. So when we're looking at this, you need to be able to control the wet bulb temperature, the relative humidity, and so we tend to have a separate system. So the sophistication is, this is an ice grinding machine. You get big blocks of ice, put them in, and it grinds it to give you ice crystals that can get injected. You've got a spray bar here if you want to add some extra moisture into it, and then it goes into your test specimen. But this isn't closed loop, so you don't, in a conventional wind tunnel, icing wind tunnel, the relative humidity goes to 100% quite quickly. But in these, they can control it because it's not going around the loop. So this has been a very quick overview of some of the challenges. So there's a range of challenges ranging from the atmosphere modelling itself to the splashing of droplets. And this has only provided an overview of some of the issues related to the modelling and testing aspects. Beyond this, there's other issues. So there's the ice protection systems, there are heaters in the leading edge. You can see this is covered in run-back ice, which is very thin fingers of ice that can form, which isn't great for aircraft runs. Possibly not a safety issue, but increasing the drag. And then there's other unusual forms. Swept wings have got what they call lobster tail ice, which looks like lots of lobster tails put together. And so trying to model those sorts of structures, going towards probabilistic type methods in terms of probability of freezing. And I think it's a disclaimer again that it wasn't all my work. And then there's a picture of me stood next to a model. So, thank you.
Okay, questions?
You didn't speak about the material effects, so the ice-phobic materials, or all the work on that. So is it, how the ice or the water can stick on the plane? Are there issues also on that?
Yes, so there's quite a lot of work being done at the moment to look at ice-phobic materials. So looking at thickened design surfaces. It's going to stick, it's just to make it low adhesion. But the problem is they tend to be soft surfaces, and we've tested about 20 and none of them have survived being, they have to go into a test, a rain erosion rig, and that's I think 3 millimetre droplets at 300 metres per second, and after about 10 minutes they're not there anymore. So.
Any other questions? Okay. Oh.
Yeah, I have a basic question. Why does water cause a sticking effect?
Why does it cause?
Why does the super cool water that appears that cause sticking effect? I think you said somewhere that water would cause sticking effect.
as in sticking to the surface?
Yeah.
Well, and because it freezes on impact, so with the rime ice, it freezes instantly on impact, so it sticks to because most of the surfaces are aluminium, but then at warmer temperatures it runs back a bit and freezes quite further out.
So it's basically water changing to ice that causes sticking.
Yes,
not
because this is super cooled water, so the water can be anywhere down to minus 25 degrees C, but it's not ice, it's still water. It needs the nucleation to make it change into phase change, so that's when it impacts the aircraft in change.
Okay, let's just thank Ian again for a very nice talk.